Okay, so we're going to work on section 14.8, which is Lagrange multipliers. Lagrange multipliers helps us find a max or a min on a surface z equals f of xy, like this. But not a global max or global min. What we're going to do is we're going to constrain points x and y to some curve. So I'm going to grab a curve and put it down in the xy plane. That curve is going to be defined implicitly. So let's say that that guy is g of x, y equals some constant. So it's just an equation in x and y where we move all the variables over to the left. Okay, you can also view this as a level curve for g. Whenever we have a function of two variables and we set it to a constant, we call that a level curve for some other surface, not f of xy, but a different surface. But we're thinking of it as a constraint curve right now. Now I'd like to project that curve up to the surface. So I'm going to draw some vertical projection lines from that curve up to the surface, like this. And then I've already drawn a little bit of a projection here. I'm going to move that up to the surface. Okay, so that curve is supposed to look like it's sort of projected up vertically to the surface itself. I'll add a little more detail to this and maybe that'll help you see it. And nothing like a perfect drawing, of course, but there it is. Okay, so we want to find max and min points. So, for example, at the highest point up here, this is a max on the surface. Z equals f of xy. Where you're only allowing x and y to be subject to the constraint curve, which is that g of xy equals c. So let's say where the point xy is subject to a constraint g of xy equals c. So we're only allowing points to be on that solution curve down in the xy plane. Sorry, that constraint curve down in the xy plane. Okay, so how can we find that? There are several steps to get us to that point. So let's go ahead and begin. First of all, we're going to parameterize the constraint curve. So we're going to parameterize it as r of t equals x of t, y of t. Okay, where t ranges over some domain, and I'm not going to guess what that might be. And so by parameterizing that, basically what you're doing is you're saying every point on this g of xy equals c. Here's 1 point. Okay, that's an x of t, y of t. So let's just say that point right there is x of t, comma, y of t. And since it's on the constraint curve, we know that g of x of t, y of t has to be equal to c, because these points are on the curve, so they have to satisfy the equation of the curve. With that expression, we're going to apply the chain rule to just show that the gradients to g, which are gradient vectors, are always perpendicular to g. So let's take that moment real quick here. Let's do the chain rule. So the derivative with respect to t of g of x of t, y of t, will be derivative with respect to t of this constant c. Of course, that'll be 0. And if we use the chain rule, we get gx dx over dt plus gy dy over dt equals the derivative of the constant, which of course is 0. And we like the chain rule because it looks like a dot product. So if you break it up, you can look at gx comma gy as one vector in the dot product, and that's being dotted with dx over dt, which is x prime of t, comma dy over dt, which is y prime of t. Okay, and that dot product is 0 for all t. Okay, now this first vector here is called the gradient of g. And the gradient is also referred to as the total derivative because it combines all the partial derivatives into one vector. The other vector is just r prime of t, if you remember r up above. Okay, so this is r prime of t. And this tells us that the gradients of g are all perpendicular to r prime of t. Okay, this is for all t, which is another way of saying everywhere on this curve the gradients are perpendicular to r prime. But you also might note that since r prime is tangent to the curve, that tells us the gradients of g are perpendicular to the constraint curve, which is g of xy equals c. And this is always true. Okay, that is something we said previously. that gradient of any function of several variables is always perpendicular to level curves for that function. So you say g of xy equals c. Wherever you set a function of two variables to a constant, those are called level curves. Now I think I'd like to make sure this point is clear. So what I want to do is grab this little level curve here. So I'm going to try and just copy it and paste it down here. And I want to kind of look at that thing in the xy plane. So maybe I'll do, let me see, x is going that way. So this actually is going to get turned vertically. That's kind of strange. Let's do it this way. So I think this curve is rising up sort of like this. Remember, the x-axis is here, and we can put it up above in the diagram. And it kind of rises up and kind of curves in toward the y-axis as it goes up. Like that. And so this curve is g of xy equals c, and of course, since it's an implicitly defined curve, it doesn't have, y does not have to be a function of x. The only thing I wanted to just kind of bring out again is this statement of the gradient of g being perpendicular to this level curve of g. So gradients will always come out like this. And I'm just sort of imagining which side they're on, and of course that would depend on the function. Okay. Okay, so each one of these guys is a little gradient of g depending on the point. Okay, but they're all perpendicular to that curve. Okay, so now next we want to subject our function z equals f of xy, which is, after all, what we want to maximize, subject to our constraint. Let's do that. Let's, and this is like our second part of this development. Let's subject z, which is our function of x and y, to the constraint g of x, y equals c, which is parameterized by, which makes it easier, by r of t, which has components x of t and y of t. Okay? So if we do that, we'll have z equals f of x of t and y of t. Now we're only evaluating z for values of x and y that are constrained to the curve. Okay, if we want to maximize this, then we can just take a derivative. And maybe I should say, if we want to find max-min locations, we can take a derivative. Now this would be an ordinary derivative, because there's really only one independent variable. So let me just demonstrate that. So you would do the derivative of z with respect to t. So that would be the derivative with respect to t of f of x of t, y of t, and of course this is another chain rule, so we'll do fx times dx over dt plus fy times dy over dt, which is equal to fx comma fy as a vector dotted with x prime of t comma y prime of t and let's come back up here and say that this is equal to the gradient of f dotted with r prime of t, which must be 0 at max or min points. Okay, so this tells us that the gradient of f is perpendicular to r prime of t at max min points. So what we've got out of all of this is that the gradient of f is perpendicular to the gradient, to r prime at max mins the gradient of g is perpendicular to r prime always, which tells us that the gradient of f is parallel, because they're both perpendicular to the same vector, it's parallel to the gradient of g. Okay, now that doesn't make them equal, but it does tell us that one, because they're parallel, you can scale one to make it equal to the other. So you could say the gradient of f is equal to some scalar multiple, and we use a lambda that stands for Lagrange multipliers. Okay, so lambda, I guess you would say, is the Lagrange multiplier. So the gradient of f is some scalar multiple of the gradient of g. Now, if we put this together with our constraint curve, this becomes a system of equations. All right, so if you put in the constraint curve, g of x, y equals c, look just at these two statements here. Gradient of f equals gradient of g. Actually, that's a vector equation, so it's multiple equations. If f and g are functions of two variables, then the gradients have two components. So the gradient of f equals lambda times the gradient of g is actually two equations with three variables. The variables are x, y, and lambda. Three variables in two equations is not enough, but if you throw in the constraint equation, g of xy equals c, now that must be imposed because we need to force those points to be on the constraint curve. Then you end up with the third equation in those three unknowns, and that's the method of Lagrange multipliers. You solve the system of equations, which can be quite ugly, and then you've found those locations where the max or mins may exist.
So here's the method of Lagrange multipliers. So you're trying to optimize z equals f of x, y, subject to the constraint g of x, y equals c. Okay, so again, this becomes sort of a cookie cutter, cookie bookie type of way to do this. You would just solve the system. Gradient of f equals lambda times the gradient of g. So that's actually, if it's two dimensional, then that's actually two equations there because each component of the vector makes its own equation. So what you have there is two equations and three unknowns because lambda has been introduced. So you need another equation. The third equation is just the constraint of xy equals c. Okay, and that'll give three equations and three unknowns. In higher dimensions, you know, a 3D version would look like gradient of f equals lambda times gradient of g. Now, if there's three variables there, they would be x, y, and z, and then lambda would be the fourth variable. So that's four variables there. That's actually, and you're looking at three equations because the gradient has three components. That makes three equations there, and the fourth equation would be g of x, y, z equals c, and that's a surface. Okay. So let's do some examples now. That's all you need to know in terms of how to do Lagrange multipliers. You just have to be really careful. And I should say, you would classify the solutions, let's say solution critical points. I'd say any way you can. And that is not very helpful. But we don't really go into new material for classifying because, you know, it may be that the constraint curve is one-dimensional. And if it's one-dimensional, if it's just a line, then it's really a one-dimensional problem. You could actually boil it down to one independent variable. So you could use the second derivative test or first derivative test to classify these points. So, you know, but we don't really spend a lot of time. Also, the other thing is sometimes these curves, these constraint curves, are not infinitely long. If they are finite in length, then they are closed and bounded, and you can classify absolute maxes and absolute mins like we did on the last discussion that we just had. Okay, so let me go ahead and let's do an example. Let's see, it's 747. We're doing fine. Okay, so here's my first one. F of x, y, this looks pretty easy. It's 3x plus y, subject to a constraint that x squared plus y squared is 10. Oops. Okay, so 3x plus y is just a plane. Let's see if I can sketch this. And of course, x squared plus y squared equals 10 is a circle. So there's my constraint curve down there. It looks like an ellipse. That's a circle. Okay, and then I'm going to put a plane up here. And I'm not trying to be real precise right now. I think I've done better pictures in my life, but I'm going to go with this. The constraint curve is down in the xy plane. Okay, so that's my g of x, y equals c. And then projected onto the surface here, you'll have, that's going to be an absolute absolute max. And down here is going to be an absolute min. Okay. So I already know what I'm going to get out of this problem. Any questions? I'm going to get 2 points. And by the way, I can call them absolute maxes and absolute mins because that constraint curve is a closed region. It includes its boundary. It doesn't have an interior. It's all boundary. But because it contains its boundary, it's closed. And it's bounded because I could draw a circle around it if I wanted to. And if a region is closed and bounded, then function can have an absolute max or an absolute min on it. So we're guaranteed for that. So I can see them. I'm expecting one of each. Okay, any questions? All right, so let's do the gradient. So the gradient of f, just as a reminder, has just partial derivatives in it. So it's called a total derivative as well. So it's just fx comma fy. So fx is 3, fy is 1, and we're done. Okay. The gradient of g is, of course, gx, gy. Now, g is the constraint curve, so maybe I should highlight that. This x squared plus y squared is g of xy. Okay, so that should be 2x, 2y. Okay, any questions out there? All right, now the Lagrange multiplier method says if you want to find the max or min subject to the constraint, then the gradient of f is going to be some multiple of the gradient of g. Of course, that lambda is an L in the Greek alphabet, and of course that stands for Lagrange, who apparently is the guy credited for coming up with this. All right, so let's see here. Gradient of f is 3, 1, and this is equal to lambda times the gradient of g. That would be 2x, 2y. And if you want, you could write that as 3, 1 equals 2 lambda x and 2 lambda y. Okay. So that's 2 equations right there. Here's my 3 by 3 system. Okay, first equation says 2 lambda x is 3. Second equation, 2 lambda y is 1. And the third equation is the constraint curve. So that's x squared plus y squared equals 10. Any questions? Somehow you have to find a way to integrate the 3 equations. Hopefully get some sense out of it. One way is to solve the first equation for x. So you'd have x is 3 over 2 lambda. And the second equation is giving y, which is 1 over 2 lambda. And then you would plug both of those into the third equation. So x squared would be 3 over 2 lambda squared plus y squared, that's 1 over 2 lambda squared equals 10. Okay, any questions? I think I'm gonna move things around just a little bit. So, okay, so let's see here. I get 9 over 4 lambda squared plus 1 over 4 lambda squared equals 10. Of course, that says 10 over 4 lambda squared equals 10. Maybe I'll reduce that. 5 over 2 lambda squared equals 10. Obviously, lambda can't be 0. So we'll stipulate that. And now I'm going to multiply both sides by 2 lambda squared. So we'd have 5 equals 20 lambda squared. So lambda squared is a fourth. And lambda is plus or minus a half. Okay, now when you get this, you should break into cases. If you get multiple values for a variable from one equation, you need to split into cases. Okay, so there should be a case 1, case 2, and I always like to draw a line in between the cases so that nothing crosses the line. You can't borrow something from one side that comes only from the other side. These are independent cases. They cannot sort of pollute each other. Okay, so in case 1, lambda is a half. And in case 2, lambda is negative a half. Any questions? The rest is easy now. In case 1, I think, what was it? X was 3 over 2 lambda. In both cases, actually, X is 3 over 2 lambda. And if lambda is a half, I think that's just 3. Y is 1 over 2 lambda. So that's 1 over 2 times a half, so that would just be 1. Okay. And then in case 2, X is still 3 over 2 lambda, but I can't use anything from case 1. I'm just using the equation from before. Okay, but lambda is a negative a half, so this is going to be negative 3. Y is 1 over 2 lambda. Lambda is negative a half, so that'll be negative 1. So your points are 3, 1, and negative 3, negative 1. Okay, so just going to pause for a second before I go on. And feel free to, unmute yourself or type a question. Okay, so we've got this function that's defined over a closed and bound region, which is the constraint curve. So f is defined or constrained. How about that? To a closed bounded region. Oops. Which is the constraint curve. So it has an absolute max and min. Okay, so you just evaluate the points. And so f at 3, 1, f at negative 3, negative 1, you got to go back to the definition. F of xy was 3x plus y. So this will be 3 times 3 plus 1, and the other will be 3 times negative 3. What was it, 3x plus y? Yeah, so minus 1. So this is going to be 10 or negative 10. So you've got your absolute max at 10. And your absolute min at negative 10. And that's it. I took a tutorial as it's just staff development a few years ago, where people were using Lagrange multipliers to optimize the motion of a robot arm that had over 100 equations and 100 unknowns when they were solving the Lagrange multipliers. And the robot arm has lots of constraints in motion, so given that it has constraints in terms of where it can move, it makes sense to use a Lagrange multiplier to optimize the amount of energy it uses or whatever as it moves around. So that's a Lagrange multiplier problem. Fascinating. And this is actually really important. It's used in lots of different optimization problems. Okay, waiting for questions. Wonder if we could do another, just so you can see. I'm not going to prove the next one, but I want you to see Lagrange multipliers. You can do more than one constraint. So like 2 constraint curves. So let me explain what's going on here. So this is Lagrange multipliers. With 2 constraints. So you can have more than one constraint on the system that you're optimizing. Okay, so we want to optimize f of x, y, z. So this is something that could be anything that's moving in 3-dimensional space, but now it's being constrained with 2 constraints. So the first would be that x, y, z is constrained to the surface g of x, y, z equals c. And then also those points are constrained to another surface, h of x, y, z equals, let's say, k. So if both of these surfaces are constraint curves, then x, y, z is constrained to be on the intersection of these 2 surfaces. Okay, so note x, y, z is constrained to the intersections of these surfaces. Okay, so I'm going to just pause for a second because I saw a question. Okay, so basically the process is we want to solve the system
and it's similar to the one constraint Lagrange method, but here you're going to do the gradient of f equals lambda times the gradient of g. But now there's another constraint, so you do the same thing, but the multiplier has to be different. So we're going to use mu times the gradient of h, that way. So that's actually, if f is a function of three variables, then that's three equations right there, because the gradient vectors have three components. So that's three equations, but now there's five unknowns. The other two equations are the constraint surfaces. Okay, you just have to solve that system, and that's the Lagrange multiplier method. Okay, so we're going to do a quick little example here. Okay, so the system has f of xy z is equal to yz plus xy. Seems simple. We have two constraints. First, that x times y has to be 1. And second, that y squared plus z squared has to be 1. Okay, so the first surface, xy equals 1, is going to be our g of xyz equals 1. And the second one is going to be h of xyz equals 1. So those are the constraints. XYZ has to be a point on both surfaces, so that'll be the intersection of those two surfaces. Okay, let's go ahead and do our gradients. So gradient of f is, of course, with three components, fx, fy, and fz. And taking these partial derivatives, fx is y, fy is z plus x, and fz is also y. Okay, now the gradient of g is going to be gx, gy, and gz. So gx is just going to be y, gy is x, and gz is 0. There's no z in g. And then, of course, gradient of h is going to have its three components hx, hy, and hz. And h with respect to x is 0, with respect to y is 2y, and with respect to z is 2z. Okay. Now, the equation for Lagrange multipliers, the first equations, is that the gradient of f is lambda times the gradient of g plus mu times the gradient of h with two Lagrange multipliers. So we probably should work that out. The gradient of f is up above, so maybe I'll just copy and paste that. So here's gradient of f coming down. There it is. So that's equal to lambda times the gradient of g, which I'll copy down, plus mu times the gradient of h here. Okay, and if we combine terms, it might look a little better. So the gradient of f is still y z plus x y, and that's equal to y lambda, or lambda y, lambda x plus 2 mu y and 2 mu z. Okay, and that creates a pretty big system of equations. The first equation you can see comes from the first components that have to be equal. So y is lambda y. Okay. Second components here, z plus x is lambda x plus 2 mu y. The second equation. Our third equation is that y has to be equal to 2 mu z. Okay. The fourth equation will be the first constraint function, which was xy equals 1. And then the last equation is the second constraint, y squared plus z squared equals 1. Okay, so that's our system. This is 5 equations and 5 unknowns, a 5 by 5 nonlinear system. And those are always fun. Generally speaking, it's nice to look at the simplest equations, and especially if there's something you can get 0 on one side and factor with the other side. That's probably the best way to go. So real quick here, that first equation says that y is equal to lambda y. Probably get 0 on one side, so y minus lambda y equals 0. That factors. You should always factor rather than dividing by variables. That'll always lose information. So here you have y times 1 minus lambda equals 0. So from the first expression, y could be 0. And from that second factor, 1 minus lambda is 0, so lambda is 1. Okay? Now, if we go, when the equations split into 2 like this, you have to treat these as 2 separate cases that don't interact. Okay, so let's look at our case 1 that y is 0. Okay, and if y is 0, note the fourth equation above, that xy has to be 1. Oops. Xy equals 1. If y is 0, that's impossible. So we'll just leave it out. This is not a possible value for y. So we move on. So case 2 is where lambda is 1. All right, I don't think there's a problem with that. And let's see where we can go with that. If we go down, or go back to equation 2, this thing says that z plus x is lambda x, but lambda is 1, so I'll just write 1x plus 2 mu y. Okay, now the x's can cancel. If you subtract them out, they go away. They are not really contributing to the equation. So you can just say that z is 2 mu y. Oops, let me go back to red here. So z is 2 mu y. And that reminds me a lot of the third equation. Equation 3 says y is 2 mu z. Okay, so it makes me think we probably should solve each of these for mu, and maybe we can find a relationship between y and z. So in the first one, mu is z over 2y. And on the second one, mu is y over 2z. Really similar relationships. Okay. Now, those are both mu, so we can set them equal to each other. We can say z over 2y has to be equal to y over 2z. And it's easy enough to cross multiply that. You would get 2z squared equals 2y squared. So z squared is y squared. And therefore z is plus or minus y. Okay. Right, so we once again have an equation that's split into two statements, so you're going to have to do another case. This is all under case 2, so the first one let's call case 2a, and the next case will be case 2b. So anything from case 2 can cross into a and b, 2a and 2b, but 2a and 2b cannot cross over. Okay, so on case 2a, let's just say z is y, and 2b will say z is negative y. And we'll just see where these lead us. Okay, so if z is y, then it's a good idea probably to bring in, finally, equation 5. Which says that y squared plus z squared is 1. But z is y, so now we can just say y squared plus y squared is 1. So 2y squared is 1. Y squared is a half. So y is plus or minus square root of a half, which is 1 over root 2. Okay. That's two cases. So maybe we can do a case 2a1 and a 2a2. Okay. So in case 2a1, y is the square root, sorry, it's 1 over the square root of 2. And in 2a2, y is the negative negative 1 over the square root of 2. Okay. Z is y, so in each case you can say z is whatever y was. So on 2a1, z is 1 over the square root of 2, and 2a2, z is negative 1 over the square root of 2. Now don't forget, x is 1 over y, and that comes from equation 4 in the system. X is 1 over y. Alright, so that means x will be just the square root of 2. Okay. In 2a2, x is still 1 over y. So that'll be negative root 2. Okay, so that's all under case 2a. Case 2b is really similar. We would say bring in again equation 5, and that says y squared plus z squared is 1. So y squared plus z squared, but that's negative y squared equals 1. Now it's the same as case 2a, so 2y squared is 1, y squared is a half, so y is plus or minus 1 over the square root of 2, and we're going to have a case 2b1 and a 2b2, like that. So in 2b1, y is 1 over the square root of 2, and in 2b2, y is negative 1 over the square root of 2. Okay, now z is negative y in this case, so on 2b1, z will be negative 1 over the square root of 2, and in 2b2, z will be positive 1 over the square root of 2. And as before, x is 1 over y. So in 2b1, x will be the square root of 2. Y will be, in 2b2, x is the negative square root of 2. Okay, so it looks like we have 4 solutions in these 4 cases. So the first case, 2a1, just has everything positive. X is the square root of 2. Y is 1 over the square root of 2. And z is 1 over the square root of 2. Okay? Then in case 2a, x is the negative square root of 2. Y is negative 1 over the square root of 2. And z is negative 1 over the square root of 2. Okay, now we're on case 2b1. X is the square root of 2. Y is 1 over the square root of 2. And z is negative 1 over the square root of 2. And the last case is 2b2. X is negative root 2. Y is negative 1 over the square root of 2. And z is positive 1 over the square root of 2. Okay, so now I've pasted in an image of the constraint surfaces. So just as a reminder, one of the constraint surfaces is xy equals 1. That's a hyperbolic cylinder. And of course the other surface is a circular cylinder. That gets y squared plus z squared equals 1. Okay, so and then when we require both constraints, then you're requiring that points be on both surfaces. And the intersection of those two surfaces, therefore, is where the points must lie. So the constraint is the intersection of the two surfaces. And as before, this intersection is a curve. Okay. Now, we are not looking for maxes and mins on this constraint. We're looking for maxes and mins for the function f, which is not pictured anywhere here except for the fact that we've found locations that are possible max-min locations. And we can label these if we want. So this point right here is the root 2 1 over root 2 and negative 1 over root 2. And you can sort of identify the rest of the points. Root 2, 1 over root 2, and 1 over root 2 is going to be this one here. Of course, the other 2 points are back there as well. Those have negative x coordinates. And I don't think I can squeeze those in, but you've got, or the coordinates in. But maybe we can identify this way. So this top point here is the last one we came up with. And I think I don't want to mess this up anymore. Let's just go with that. All of these points are pictured here. And the intersection curve is not closed or bounded. So we can't use the test for absolute maxes and mins. So it gets a little harder at this point, and I would say that the classification is almost beyond what we're going to expect you to do, although it's not beyond something you could understand. If somebody asked me to do this, I would need to parameterize these curves. So remember the surfaces are x, y equals 1 and y squared plus z squared equals 1. Now, that's in the yz plane, the second constraint is just a unit circle. So it makes sense to make y cosine theta, z sine theta, and then the first curve, or this first surface, tells us that x has to be 1 over y. So this would be 1 over cos theta. Of course, that's going to be secant theta. Okay, so that tells us that the intersection curve can be parameterized by an r of t. So if x is sec t, then y would be cos t, because y is 1 over x, and then z would be sine t, like that. And if we want to optimize f subject to this constraint, then you just have to substitute this in and make it a function of t. So to optimize f of x, y subject to this constraint, then you kind of have to do what I did in the development. We just substitute here. Okay, so you would have z is f. Oh, and I said f of xy, but I meant f of xyz, because this is a function of 3 variables now. Okay, so z would be f of x of t, y of t, and z of t. And then just stepping back, we'll remind ourselves what f was. That's a page back or so. Way up here, f of xyz is this. So let's slide down. And just remind ourselves. So if we substitute everything in, yz is going to be cos t sine t. Plus xy so x times y is sec t cos t. Of course, the secant is the reciprocal of cosine, so that's just going to be 1. You can use a double angle formula and say that this is actually 1/2 of cos 2t. I'm sorry, sine 2t. So now z is just 1/2 sine 2t plus 1. Like that. And then you can optimize this. We already know that setting dz over dt to 0, this will yield the solution points above. I'll say the same solutions as the Lagrange method. Okay. We could use the second derivative test here to classify those points. With, I guess we would do the second derivative of z with respect to t to classify the points. And again, I don't really want to go any further than this because, as I said, while this is not beyond your ability at all, because this is just really doing a Math 180 problem, I would say it's beyond what you probably have time for and what's actually reasonable. So mostly the Lagrange multiplier problems that get sort of involved and complicated like this one, and problems that you could probably spend an hour on, that just goes too far. I think you could find and classify all these critical points, But I think we'll just sort of restrict it to when the constraint curves are closed and bounded, meaning they're not infinitely large or infinitely long, that they're constrained to some finite amount of space. When that's the case, then you can go ahead and find the absolute max and absolute min, but I think we'll just ignore those local max and local min points with the constraint curve. Okay, and I think that's all I really wanted to say about all of this, so let's leave it at that. Good luck.